So now we get to talk about modulation, and I love talking about modulation. I've been teaching at Cisco since the late 90s, and so I've taught a range of RF engineers to software engineers to product marketing. And a couple of years ago, one of the really technical architects came up to me and said, I've had people explain modulation to me maybe 20 times, different instructors, and I've never understood it until Avril, you explained it. So I'm really hoping that this will be easy for you to understand as well. So the technical way we talk about it is we could say we're going to take your digital data and we're going to encode it onto a carrier signal. But the simple way of thinking about that is simply your ones and zeros represented in waveforms, because what goes out over the air is not ones and zeros, but is waveforms. And when we look at a waveform, we can vary the waveform in three ways. We can change the amplitude of the waveform, i.e. we can have a big wave or a little wave. We can change the frequency. When I talk about the frequency, I'm talking about the number of cycles per second, the number of times that waveform goes up and down per second. So I can slightly incrementally increase the frequency, slightly decrement it a bit, and I can distinguish between your ones and zeros. I can also change the phase of the wave as well. And so if I can change the waveform, different waveforms can represent different combination of ones and zeros. And it's really as simple as that. So let's take a closer look. Okay, so let's talk about amplitude. And here you can see I have a big wave here. I'm varying the amplitude, and now I'm sending a small wave. And so I can say, okay, this represents a 1 and this represents a 0. And so again, by changing the amplitude, which is the power of the waveform, I can distinguish between ones and zeros. Also, I can change the frequency. See how here these waveforms are going up and down, the number of cycles per second, each up and down is considered one cycle. So if I send less cycles per second, then that can represent a 1. And here, see how I'm going up and down a lot more often per second. So there I say, okay, that's a 0. So I can change the amplitude or I can change the frequency. The other thing I can do is change the phase. So here you can see I'm going up, and I can say, okay, if it starts with an up, is a 1, and if it was to start coming down here and then going up, I could say, oh, that's a 0. So I can change my amplitude, the frequency, and the phase to distinguish between your ones and zeros. Now, what's really exciting here is not that I have to choose one or the other, I can actually combine them. And that's what we do on most modern radio that's used for sending data. We normally combine amplitude shift keying with phase shift keying, and we call that quadrature amplitude modulation. So, and I'm going to show you that on the next few slides. So let's start with something simple, binary phase shift keying. This is used in your cellular networks, in WiMAX, is used in Wi-Fi wireless LANs, and it's actually used in Bluetooth. So it's a very common technique for representing your ones and zeros, regardless of what type of wireless network it is. And again, it's a phase shift keying. And here I'm representing two waveforms. And if I have two waveforms and they're different, then I can distinguish between two bits. And so here you can see, if I come up here, I say, okay, this is a 0. And then in my next bit period, I'm going to start downwards. So I've done a 180-degree phase shift, and I say that represents a 1. So what I'm doing is every bit period I'm changing the phase of the waveform in order to distinguish between your ones and zeros. Again, binary phase shift keying, 1 bit per waveform. The correct terminology is 1 bit per modulation symbol, but I always like to say 1 bit per waveform because it's conceptually easier to understand. Now I can keep going. Instead of having a phase shift of 180 degrees, I can have a phase shift of 90 degrees. Now if I have a phase shift of 90 degrees, you can see therefore is that I can come up this way, I can have one coming down, one like this, and then one like this. So what I've got now is 4 different phase shifts, 4 different waveforms. And therefore, if I have 4 waveforms, then I can represent 2 bits instead of 1. Right? So I'm now sending 2 bits per modulation symbol, or 2 bits per waveform, which means I doubled your data rate. So from going from BPSK to QPSK, I can send twice as many bits in the same spectrum and double your data rate. And you say to me, well, why don't you keep going? Why don't you go to 45 degrees and have 8 waveforms and therefore 3 bits per waveform? And I can indeed do that. But it's actually better when we start getting up to higher data rates to move to a quadrature amplitude modulation. So rather than just increasing the phase differences, I'll do a combination of phase and amplitude. And to represent that, I've put it on a polar plot. And so what you can see here is the amplitude is the distance from the origin out to the dot. So each one of these represents a different amplitude. And then the phase is the distance around here from the x-axis, like this. So each one of these dots has a unique combination of phase and amplitude. And so now I have 16 dots, right? 16 unique phase and amplitude, which means I can represent 4 bits. So this bit here, this dot here, represents 0, 1, 0, 1. This dot here represents 0, 0, 0, 0. Well, then I can keep going. And then we go to something called 64 QAM. And now I've got 64 dots. And so this dot here, for instance, represents 0, 0, 1, 0, 1, 1. This one next to it here, 0, 0, 1, 0, 1, 0. So I just read off these numbers here, and so I'm now able to send 6 bits per waveform. And you say to me, oh, Ava, why don't you keep going? Well, there's a problem if I keep going. You'll notice here that the dots are getting closer and closer together. So if I'm operating in a noisy environment, maybe my signals are bouncing off walls and people's bodies and people are moving, etc., it's quite possible that my signal will kind of come over here. And then I have to kind of guess, is it this dot or is it this dot? And if I guess wrong, then I've got the wrong bits and I'm going to have a corrupt frame. And so I'm great as long as my signals are coming in fairly close to where this dot is. But if I move into a more difficult RF environment where I start getting errors because I'm guessing wrong as to which dot it is, then I have to go from 64 QAM back to 16 QAM. Because you can see if I got a dot coming in here, I can say, oh, it's probably this one. And then if I start getting into a more difficult RF environment and 16 QAM is giving me error, then I'll drop back to QPSK. And if that gives me error, I'll drop back to BPSK. And if BPSK gives me errors, then I'm out of coverage. I can no longer communicate with the radio because I've now got such a difficult environment, I'm not able to recover my signals at all. Now this is the picture that now brings that all together for you. So what you would have observed If, let's say, you've got 802.11g radio at home, your wireless LAN is 802.11g, and you've noticed that if you're close to the access point, you can get up to high data rates. You can get up to 54 megabits per second. And as you walk away, your data rates drop to 48, to 36, to 24, all the way down to 6 megabits per second on the edge of the cell. What's happening there is that when you're close to the access point, you're able to use 64 QAM, you're able to get to the higher data rates. Your RF conditions are good, maybe you've got line of sight, you're close to the access point. As you move away or you move into more difficult RF environments, it's more difficult to recover your signal. You have to drop to 16 QAM, to QPSK, and then right out on the edge of the cell coverage, you need to drop down to BPSK, 1 bit per waveform, and at that time you'll be down at 6 megabits per second. And if you go beyond that, you'll be out of coverage of your wireless LAN and you won't be able to communicate with it. So this is what we mean by modulation. As you move around, your modulation changes. Cisco calls this rate matching. If you hear those terms, rate matching. You're matching your data rate to your RF conditions. Good RF conditions close to your access point, higher level of modulation, higher data rates. Further away, lower modulation, lower data rates. And believe it or not, not only does the wireless LAN Wi-Fi operate that way, but the same thing is true of your cell phone and WiMAX. All of these technologies that are doing high-speed data operate in the same way. The closer you are, the better your RF conditions, the higher the data rate I can get. As I move away, my data rate drops as my RF environment deteriorates.